And welcome to Topic 1.
Factors and products!
Our first topic is all about prime factorization. We've talked about factors and products of integers in previous years. This year, we're going to be involving variables. But in this first little bit with prime factorization, we're just focusing on integers for a bit. So let's talk about what prime factorization actually is.
Prime factorization is writing a number as a product of its prime factors. So for example, the number 20 is a product of the prime factors 2 times 5, which we could write as 2 squared times 5, just for a little bit of space-saving format. So there are multiple methods that we could actually do a prime factorization. And the first one that we're going to take a look at is factor trees. So what that is we start with the number at the top, and then we start breaking it down into the product of any two whole factors. It doesn't have to start off as two whole prime factors, but any two. And then we keep on breaking it down until we're only left with prime numbers at the bottom. So just to recall, prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, so on and so forth. So for this example here, we look at 288. And 288 can be broken down as the product of 2 times 144. So as you can see, we break it down with these two arrows, 2 and 144. Notice that we've circled 2 because 2 is a prime factor and it can't be broken down further. We can't keep on going because the only thing we'd keep on getting would be 1 times 2, and that is useless to us. 144, however, is not prime, so we can keep on breaking it down. So the first product that comes to mind might be 12 times 12. And we break that down, and when we get to these 12s here, those aren't prime either, so we could continue to break them down. So 12 is a product of 3 times 4, and here we go with 3 being a prime number. That can't be broken down further, but the 4s can. So the 4s we break down as a product of 2 times 2, and we end up with all these circled guys as our prime numbers. So we take those values and we can write it out. We could say 288 is the product of 2 times 2 times 2 times 2 times 2 times 3 times 3. Usually we write it in ascending order. So we usually group all the 2s together, then do all the 3s. And if there's 5s next, we do those, then 7s and 11s and 13s and so on. But instead of writing it out, so that we have this long multiplication statement, we can actually simplify and say, well, we have the product of 2 5 times. We could say 2 to the power of 5, and then 3 to the power of 2.
I'm so curious about this 12. You said 3 times 4, but in my head it's 6 times 2. Does that even matter? Would I get a different answer?
No, that's the thing. So if we looked at someone else's work and thought, well, if I broke down 12 and I think 6 times 2, we could actually continue the tree and still end up with the same results. So, just for funsies here, let's pretend, well, maybe I will do this. Let's pretend none of this ever happened.
Whoa.
And we did think about 6 and 2. If we did that, our 2s are still prime numbers, so we can't break those down any further, but the 6s can. And what do you think when you see 6?
Oh, me personally, I see 2 times 3.
2 and 3. Perfect.
Yes.
And when I do that, the 2s and the 3s are also prime values. If you look at our final answer, we notice that we had 1, 2, 2, 2. Oh, the pen's not working.
Working very selectively.
Oh, there you go.
Interesting.
Oh, I think it's because of the white in the background.
Yeah. Interesting.
Oh. Okay, let's try it this way. So you can see that we still have 1, 2, 3, 4, 5 twos, just like we have here, and 2 threes.
Wow.
Just like we have there. So it doesn't actually matter how you break it down, as long as you keep on going until you end up with your prime factors.
That's really wicked cool. I didn't realize math was so much fun.
Oh, this is just the beginning.
Maybe I'll try an example. Oh, here's a 12, and I will use a factor tree specifically to determine the prime factorization of that value. So this 12, I mean, I used to see 6 and 2, but I guess I could just say it's 3 and 4 just as well. If I know how to draw the number 4, nailed it. 3 is prime, 4 is not. 4 is 2 times 2. So it looks like that one's all done. I could say that 12 is equal to 2 times 2 times 3. And that is my expanded form. Or I could say that 12 is 2 squared times 3. And this is sometimes referred to as power form. That's an interesting... How did that happen? Do you see that? Do you see that? What? It turned blue. I've never seen that happen before. That was incredible.
All right, and we could do other examples here as well. So if I'm looking at this 75, the first thing that comes to my head is 3 times 25. You might see 5 times 15. It doesn't actually matter, like we talked about before. 3 here is prime, but 25 isn't. And 25 I see as 5 times 5, and both of those 5s are prime. So my final answer here in expanded form would be 75 is equal to 3 times 5 times 5. Or we could write it in power form as 75 is 3 times 5 squared. Something to keep in mind real quick here is when you noticed up here in this example, it said 2 to the power of 5, and then we didn't have like a multiplication symbol or anything inside, because we could tell that that exponent kind of broke up the value. Whereas down here in this example we just did, if we didn't have that multiplication sign, it would look like 35 squared. And that's not the same thing. So please make sure that if there's no exponent, right, because we know there's an exponent of 1, but if we're not writing 1 down, then we're making sure to have a clear multiplication sign in between those two values. Cool?
Sounds cool to me.
All right, take it away.
Okay. Ooh, 18,000. There's so many things this could be. I see 18 and 1,000. So that's what I'm going to go with. 18, maybe that's like 9 and 2. And I'm just going to keep breaking this side down until it's completely done. Whoa. And then I can tackle this other one. 1,000, that's like 10 and 100. 10 is 5 and 2. That's done. And there's this other 100. That's 10 times 10. And each of these 10s is going to be 5 times 2. Those are done. Let's figure out what I've got here. For 2s, I've got this one, this one, this one, this one. So I've got like 4 2s. And I've got how many 3s? There's a 3, no other 3s. So it's the 2 3s, and then how many 5s am I dealing with? That's 2, 5. So 5, 5. So I got 3 5s. So 5 to the power of 3. That is what we'll call that one.
All right, this next one here, the first thing that I can see is that it has to be divisible by 25 because it ends in that 25. So I know it's going to be 25 times something, but off the top of my head, I don't actually know what that is. So what I'm going to do is I'm going to do the long division off on the side.
Can't I just use a calculator?
Well, it's good to practice your math skills, but also some of these units are going to be calculator free.
What?
So getting in the habit of doing the math on the side is going to be really good for us. So 25 doesn't go into 5, but 25 goes into 55 twice. And that gives us 50. 25 goes into 51 twice. 25 does not go into 12. But 25 goes into 125 5 times. So my product here is 25 times 2,205. I'm going to go ahead and break down that 25 into 5 times 5, and those are both prime. My 2205 here, I know is going to be divisible by 5 because it ends in 5, which is nice and prime. But I don't know what it actually is. I'm going to move that to be small now.
Oh, that's adorable.
Right? So, I can see how many times 5 goes into 2,205. 5 goes into 22 4 times. It goes into 25 times. And it goes into 5.
Does it?
Oh, sorry. Woohoo. I was looking at the 4 at the top. It goes in. Go away, go away, go away. 4 times. Good catch.
That's why I'm here.
And it goes into 5 once. So I get 441. And 441 is still not prime. I know it's not going to be divisible by 2, but because of the sum of the digits adds up to 9, I know it will be divisible by 3. So I'm going to give that a go. Again, I'm going to shrink this down to be nice and cute. Alrighty. Now, 3 going into 441. 3 goes into 4 once. 3 goes into 14 4 times. And 3 goes into 21 7 times. Whew. 147. Now we're cooking. All right. And so now I have this 147. Personally, the first thing that I look at, again, it's not divisible by 2. Is it divisible by 3? I'm looking at the sum of the digits. And we have 1 plus 4 is 5, plus 7 is 12. So yes, it will be divisible by 3. And we keep on plugging away. Oops. Let's make this guy nice and small and cute. Put him in our stack of equations here. All right, so 3 into 147. 3 goes into 14 4 times. 3 goes into 27 9 times. Sweet. Oops, I wasn't doing arrows before. So I got 3 and 49. All right, and 49, the first thing I think of is 7 times 7. Oh, and both of those are prime. Whew! So that was a little bit of work, but that's okay because we are awesome. So
everything is awesome. Everything's cool when you're part of the team.
All right, so here I have 55,125. There's no 2's here, but I have 2 3's, so I can write 3 squared. I have 1 2 3, 5 cubed, and then 1 2 7 squared. So I could write 55,125 is equal to 3 squared, 5 cubed, times 7 squared. Awesome. So that's how we do some factor trees.
Factor trees do take up a bit of space. We can see this really starting to take up room. And we can use a line-by-line method, which is basically exactly the same in terms of what factors we see. We just really avoid having these lines over and over. So we have a little bit of room to save space there. But otherwise, it's the exact same thing. We're just looking for what we can break down a number into and going from there. So just as above, we said that 288 was 2 times 144. I can't. Oh, there we go. There's 288 as being 2 times 144. And just as with the factor tree on the previous page, we said, well, 144 is the same as 12 times 12. We have that here as well. So we keep breaking every single piece down until everything's prime. This 12 turning into 3 times 4, and this 12 turning into 3 times 4. So that's where everything in that line comes from. And then the 4s each turn into 2s. Green, where are you? So that's where those 12s go. And then in the end, if we want to write this in more of a power form, we can note that we have a certain amount of 2s, and we've got a certain amount of 3s. There are 5 2s and 2 3s, therefore we have this result. So again, very similar, we're just not drawing these lines of the factor tree. We're not seeing the tree directly, but it's still kind of there.
Yeah. So we can go ahead and look at the same values that we were doing before, but now doing the prime factorization without that factor tree, so using the line-by-line method. So I'm going to start out with my number 18,000, and just as Mr. A said before, he saw that as 18 times 1,000.
I did see it that way.
I saw it that way too. Well, that 18 I can write as 2 times 9. Right? So just so we can see that, that 18 became 2 times 9. And this 1,000, I'm going to do at the same time and say that 1,000 to me looks like 10 times 100. So I'm going to go times 10 times 100. So my numbers aren't changing, I'm just breaking them down into smaller and smaller products, or smaller and smaller factors, so that I can have the prime factorization. Continuing on here, the 2 doesn't break down into anything, but this 9 does, and 9 breaks down into 3 times 3. So the 9 goes 3 times 3. The 10 breaks down as 2 times 5. And that 100, I'm going to break it out down to 10 times 10. Just where we can see where everything's coming from. All right, continuing on in that next line, you can see my 2's all done, my 3, and my other 3, and my other 2, and my other 5 are already broken as far as they need to be. But these 2 10s can break down a little bit further. Each 10 can break down as a product of 2 times 5 and 2 times 5. So this guy is really this guy, and this guy is really this guy. Whew! Notice how much less room we used between the example up top, that dark blue factor tree, and the line-by-line method. However, everything, if you're looking across each of, can I make this smaller? Oh, sweet. If I'm looking across, ooh, I didn't want that. My bad. Try that again. If we're looking across each row, we actually have the same numbers. I did them in a little bit of a different order than Mr. A did, but the same thing. So nothing changes. So here he had 9 times 2, I had 2 times 9. but the order of multiplication doesn't matter. So it's the same thing. So when I'm expressing my final answer, I already have it in the expanded form, but I prefer to have things in power form. So if I'm looking, I have 1, 2, 3, 4 2s. So 2 to the power 4. I have 1, 2, 2 3s. So 3 squared. And I have 1, 2, 3 5s. 5 cubed.
And this last example, again, we did it up above. Maybe we can save some space. I'm looking at this. I'm seeing that it ends in a 25. So for sure, it's got a 25 in it. 5, 5, 1, 2, 5 is the same thing as 25 times something. Fortunately, someone else did the work for us way over here. It looks like it's 25 and 2205. Oopsie daisy. And we'll take each of those pieces and break them down a little bit. We'll take this 25 and say that it's 5 times 5. Ciao. We'll take this 2205 and say that it's 5 times, oh, if I had to just think about it, I'd say 441 off the top of my head. What's a nice underlining color? Yes, the slightly darker orange. And again, continuing to break that up. This 5 stays the same, this 5 stays the same, this 5 stays the same. They're already prime, but 441 can be broken down further. In fact, you know what? Let's just shake things up. I see that 9 goes in there. 9 goes in there a bunch of times. Neat. So I can say that 441 is 9 times 49. Five times 5 times 5 stays same. 9 I will turn into 3 times 3. 49 I'll turn into 7 times 7. So again, this 9 became this 3 times 3. This 49 became this 7 times 7. And finally I can wrap this up because everything's prime, and I can say that 55,125 is the same thing as 3 squared times 5 cubed times 7 squared, which we can see is same as what we had up here. So no matter which way you go about factoring this value, you will get the same answer.
Awesome. So if we're looking at the bottom here, there's actually some practice that you could do in your textbook if you so desire. So take a look at that, check that out, and we look forward to seeing you in class.
Yeah. Well, it's been a slice. Bye.
Adios, muchachos!